Okay, so what are the dangers of outliers? You might have some data and you have some data that are corrupted by really horrible noise, let's say for some reason that we don't know. Um, and we feel like this is the true trend. But if you have a lot of outliers, then you might actually substantially change the fit to the data. Okay, if you have really far away outliers, you might actually substantially change the outliers. Um, so you could, for instance, have a situation where every one of the data points follows this trend roughly, and then you have an outlier that's really far away. And if you fit a line to this whole data set, you might actually get this red line. That's possible, right? So if you make this outlier really far away, you would actually get, if you are using mean squared error to minimize, to fit the data, right? If you're fitting um, by minimizing mean squared error, you might actually get this kind of behavior. So what this suggests is that this method, where you fit to the data with the outliers and then find the outliers based on that fit, might not always work. Might work if the outliers are somewhat bad, but if the outliers are really bad, it might not actually work because the fit might be so horrible that um, the error based on that fit might not actually be a good idea to use as uh, uh, a criterion to determine the outliers. Okay, so that's important to know. But this method will work if you have mild outliers, let's say. Uh, okay, so that's something to remember. Um, what else? So there's a lot of different other ways of doing outlier removal. So first of all, once you remove the outliers, what do? You can essentially fit the data to the new data set with the outliers removed again, right? So that's an important component, and you can make sure, well, you can see if the new fit has more reasonable properties. Okay, um, hopefully it has more reasonable properties. Okay, so um, but there are other ways where instead of actually eliminating the outliers and fitting to the data after removing the outliers, you can do a variety of different things. One way is what's called weighted least squares, and I believe robust fit in MATLAB implements this. There's also a robust option in FitLM that implements some kind of weighted least squares, I believe, um, or at least a robust regression procedure. We will see a few robust regression procedures in a minute. Okay, so what is weighted least squares? If you have a regular least squares problem, what you're doing is minimizing the mean square error, which is summation 1 over n, yi minus blah, blah, blah squared. And then weighted least squares is actually putting in this weight wi. Okay, so for each data point, you can put in a weight, and with the hope that we can put in a smaller weight for data points that are far away, namely outliers, and then maybe the weights are equal to 1 for the regular data points that are within the normal sort of usual distribution of the data. Okay. Um, so that's an option, doing this weighted least squares. You can more generally, so this is actually equivalent to minimizing this quantity. So if you recall the derivation that I did a couple of weeks ago for mean squared error minimization, we actually minimized y minus xb transpose y minus xb to get the expression for b in terms of the so-called pseudo inverse. But if you want to do a weighted least squares, you have this matrix W, and if the matrix W is diagonal, then this formula is the same as this expression, it turns out, except you put in a 1 over n here, and it becomes the same as this formula. How are the weights chosen? How are the weights chosen here? The weights are chosen in a sort of iterative manner, where you first do a fit and see what the error is for the fit. And the data points that have greater error are assigned a smaller weight, wi, and you do that a couple of times. Okay. And there is a formula for this weighting that I will show in a minute that is used in typical scenarios and in a few different software. But the basic idea is that you do the fit once, you see what the error is on all the data points, and then underweight, downweight the data points that have higher error. Okay, so that would be weighted least squares, and that will give you a new fit that mostly ignores the outliers, or at least is less affected by the outliers. And then another method, it turns out, to deal with outliers, this is actually perhaps one of the better approaches, is everything else so far is dependent on minimizing the mean squared error, right? So this quantity, or 1 over n times this quantity, and so on, this thing. It turns out, obviously, that you can minimize other quantities that have this flavor, right? So this quantity takes each error, squares it, and then takes the mean, right? So why do you square the error? Because we don't want to have negative error, right? So if you only want error that is positive, right? So if the data point is away from the model, the error should be assigned a positive cost to minimize. If the error can be both positive and negative, they can sort of cancel, and you can have a mean error equal to 0. Of course, mean squared error will not be 0 if you have error, but mean error without the square can have 0 error. So you always want to make the error positive, right, by doing a square or something. So just like a square, instead of a square, you do what's called mean absolute error, right? So instead of a square, you just take the absolute value. So the formula looks like this. And this regression would be called least squares regression. This regression might be called L1 regression, or sometimes called least absolute squares regression. The least squares regression is called L2 regression because of what's called the L2 norm, which is this quantity. Okay, so I'm going to talk about norms in a separate video, but suffice it to say that this quantity where you're minimizing the absolute values is called least absolute residuals regression, or L1 regression, and the mean squared error minimization is sometimes called L2 regression, or minimizing the L2 norm, and so on. Okay, let me stop this video here, and then we'll build on these topics on the MATLAB side in a minute.